Welcome back, everyone. Today we are starting what should be the first part of a 3 or 4 part playlist on the prerequisites for Calc BC. But the thing to keep in mind with algebra is that your Calc teacher is there not to review algebra. Your Calc teacher is there to teach you calculus. So having all this stuff down will help you be able to focus on the calc easier and hopefully avoid some silly mistakes on tests. So starting with exponent rules, here we have the 4 common ones that you'll usually see. So common base A, as long as it's the same between two numbers being multiplied and those numbers have two different exponents. Some people, they multiply the exponents, but be sure to add the exponents. So you have a base A multiplying a to the x times a to the y, that is a to the x plus y. So usually you would see problems with x's instead of a's. So if we had x cubed times x to the 5th, instead of saying x to the 15th, that is x to the 8th. Similarly, if this is multiplication and that's addition, you can probably predict division yields subtraction. So numerator minus denominator, a to the x minus y. As long as the base is the same, you can do this. Usually, it's not an a, it's something like x cubed plus 5 raised to the minus 2 over x cubed plus 5, the same base raised to the 3rd, something like that. So you just subtract minus 2, minus 3, and that is equal to minus 5. X cubed plus 5 raised to the negative 5. And these two are also very similar, so some people would write this as ab to the x, but you have to distribute this x to both numbers being multiplied. So ab in parentheses raised to the x comes out to a to the x, b to the x. And similarly here we have a to the x over b to the x. This negative here, since if we write this as x cubed plus 5 to the negative 5 over 1, this is a fraction, and having this negative here just means that you put it to the denominator. And if this were in the denominator and it were negative, you would put it to the numerator. So the negative exponents, they never mean anything about having a negative out front. It's always about flipping the fraction or putting something into the denominator if it were in the numerator. So we could rewrite this as 1 over, and then it would be x cubed plus 5 raised to the positive 5, because now it's in the denominator. So these two things are exactly the same. Negatives never indicate anything about the value of the base being positive or negative. So please never write x squared or x to the negative 2 as negative x squared. Those two are not the same thing. So let's look at an example problem here. We have x to the 1/2 and x to the negative 1/2. Something I like to say about those. Fractional exponents, those just indicate that there's some sort of root. So the most common one you'll see is to the 1/2. That just means the square root, but you could have something like x to the 3/5. And what that means, if you look at the denominator of the fraction and the exponent, that indicates what is outside of the root. So this is a 5th root, if you look at the 5 there. And then the numerator of the fraction on the exponent indicates what power inside the radical is being raised to. So this is x cubed, the 5th root of x cubed. These two are the same. Just thought I would preface that. But looking at this, we just have to apply what we learned up here. So this first term right here, we can, since it's the same base x here and here, we can add the exponents. So we have 8x3 plus 1/2 is 7/2, 8x to the 7/2 minus, and then we distribute both the minus and the x to the negative 1/2 to both of these. So negative x to the 4th, and then these two are the same bases, x and x. So 4 minus 1/2 is again x to the 7/2, and we distribute this negative and this x to the negative 1/2 to this 3. We get through negative 3 x to the negative 1/2 all over x. Now we can combine like terms in the numerator. We have an x to the 7/2 here, 8x to the 7/2, and then a 1x to the 7/2. So we can combine those two to 7x to the 7/2 minus 3x to the negative 1/2 all over x. And here I would like to introduce a new concept that you will hear a lot, and that's called shaped like a heart, take it apart. So if we draw a cute little heart around this, that kind of shows you when you can use this and not. But the rule is when you have two terms or things in the numerator separated by addition or subtraction, like we have here, you can separate that into two different fractions, and then it makes things a lot easier to operate on. So that's what we'll do here. We can split this up into 7x to the 7 halves over x minus 3x to the negative 1 half over x. And now we can just use the exponent rules we learned up there and use that on these and see what comes out. Something else I'd like to say about shaped like heart, take it apart. The other addendum to that is shaped like a butt, don't touch it, which is a crude way of just saying if you have something subtracted by addition or subtraction in the denominator, you can't split it apart in the same way that you can when it's in the numerator. So an example of that, if you have 5 over 2 plus 3, obviously this fraction is equal to 1 because it's 5 over 5, but if I were to split that up like I did up here, it would become 5 halves plus 5 thirds. And 5 halves itself is bigger than 1. It's 2.5. So this obviously doesn't work. Please don't make that mistake. But continuing with this, all we have to do is subtract the exponents. These have exponent of 1. So this comes out to finally 7x to the 5 halves minus 3x to the negative 3 halves. Not too much sweat there. This will come in handy a ton though, so keep that in the back of your head. Moving on to fractions. Fractions are something you're going to have to deal with on the daily for calculus. So being comfortable with operating on fractions, flipping them upside down, adding them, subtracting them when there's not the same denominator is something you're going to have to be familiar with. So in this case, we can't add these two as it is because they don't have the same denominator. When you add fractions, the only way it works is if you have the same denominator. Obviously with like multiplication, you just multiply across, but that's not what you do with addition. So we have to somehow get the denominators to be the same, and then we can combine it into one whole fraction. So the way we're going to do that, one of the rules in algebra that you learn day one is you can do whatever you want to anything as long as to an equation, as long as you do it to both sides. And you can do whatever you want to an expression like we have here, as long as you leave it unchanged. So what we're going to do is multiply each of these terms by 1. And you may think that doesn't do anything, and you're right, but we're going to do it strategically so that we can get the denominators to be the same. So over here, we're going to multiply x plus 3 over x plus 3, which doesn't change the value of the expression because it's just multiplying by 1. And then over here, we're going to multiply x minus 1 over x minus 1, which is also equal to 1, so we're not changing it again. But if you notice, we did this because now we have x minus 1 times x plus 3 in both of these terms. And so now all we have to do is just do some foiling on the top. Some trick that I would like to impart on you is when you're foiling, sometimes it gets annoying with the mental math that you have to do for the O and the I in FOIL. So we know that the front one is 2x squared, and we know that the last one is plus 5, but then the middle one gets a little mushy. What I like to do, usually this is just an x, so you can just go minus 1, minus 5, and write minus 6x. But all you have to do is just 2x here, negative 5 here, and minus 5 minus 2 is negative 7. Hopefully that helps. Maybe that made sense. But it's just 2x squared minus 7x plus 5. And then over here we can do the same thing. So it's just 9 plus 1 is 10. 3x times 3 plus 1 times x is 9. Or 10x. So we have plus 3x squared plus 10x. 3 times 3 is 9, plus 1 is 10, and then plus 3. And now we have all this over our common denominator that we figured out, x plus 3 times x plus 1. And we just combine like terms in the numerator, and we have our one fraction. So the next one, we have a fraction nested in a fraction, nested in a fraction. It looks really messy, but all we have to do is our same strategy up here of multiplying by 1. So if we start down here, we can't add them right now because this is 1 over 1. They don't have the same denominator, obviously. So if we multiply 1 over 1 times y over y, which doesn't change it, now we have a common denominator and we can add. So this is equal to x over 1 minus 1 over, and now we have y plus x over y. And now we have what I like to call a fraction stack. This is another thing you should be really familiar with. If I have a fraction a over b over c over d, you can rewrite this as a over b, and then if we use our little exponent rules that we used before, c over d raised to the negative 1, this just means that this whole thing goes all the way back to the denominator. So these two right now are equivalent because this negative 1 indicates that it goes to the denominator. But if we use our rules that we learned before, we can distribute this negative 1 to both terms. That's still the same thing. So times c to the negative 1 over d to the negative 1. And if we have these negative 1s, it means flip it, or put it to the opposite place that it is right now. So this goes to the bottom and this goes to the top. And we end up with a over b times d over c. So we go from this nasty looking thing to this thing, which is what we're going to do over here. So if you can imagine this as 1 over 1 as a over b, and then this is our c over d, we're going to try and end up with what we have over here, but instead on this thing. So essentially all we did was took this whole denominator fraction, flipped it upside down, and multiplied it back into what we had before. So x over 1 minus, and then we take this whole thing, that's our a over b is 1 over 1, multiplied by, and then c over d becomes d over c, so y over x plus y. And now we can just multiply through instead of having a fraction stack. So this is now equal to x over 1 minus y over x plus y. And again, we don't have a common denominator here, so we're going to have to multiply this by x over y, x plus y over x plus y. Hopefully you got the hang of it so I don't have to write it out. But we have x over, and then we have x plus y over x plus y, so we just add the x plus y and then subtract the y. So x plus y minus y, and then we have the same denominator. That was the point of doing that. And there we go. And again, we have a fraction stack. We can actually get rid of these y's real quick. We have a fraction stack x over x plus y, so we have to do what we did up here. So the a over b would be x over 1, technically, and then this over here is the c over d. So we just take this whole thing out to the front, flip it upside down, and multiply it back in. So x over 1 times, and then x plus y over x. And now if you notice, we have numerator and denominator, we have x's there. We can ignore both of those, and this 1 doesn't do anything. So our final answer is x plus y. Now moving on to factoring. Factoring is another huge one that you'll do basically every day. So if this is your weak spot for algebra, you are in for a long ride. But anyway, to review, we have the difference of squares. That's something you learn fairly early on in algebra. So you just take one square minus the other. That turns into the square root plus the other square root times the square root minus the other square root. So what that looks like, the square root of this is 3x, square root of this is 4y, sorry. So 3x plus 4y times 3x minus 4y, and the reason this works so beautifully is because this negative 4 times positive 3 cancels out with this positive 4 times positive 3. So those just get subtracted from each other ultimately, and you end up with 3x times 3x minus 4y times 4y. The next problem that we have kind of looks different than what you would normally see. So what we're going to try to do though is take out something from both of these and see if we can make it look better. So factoring is sometimes trial and error. You kind of have to rinse and repeat until you find that right answer. So what I notice here though is that we have an x plus 3 and an x plus 3 raised to two different exponents. So what I'm going to try first is taking out an x plus 3 raised to the negative 1/2 and see if anything comes out of that. So we can't leave it unchanged, so I'll just take this out front, and now this becomes x, so this is still the same, plus, and then if we divide 2 times x plus 3 raised to the 1/2 divided by this, We have the same base there and there, so it's 1/2 minus negative 1/2, which is equal to x plus 3 raised to the 1. So what that looks like is, now we have this. If that sounded a little wishy-washy to you, just check this. This right here is the same as that, and this right here, if we add the 1 and the negative 1/2, we get back to the 1/2. So this is all the same thing. We haven't changed anything, we're just making it look better. But now, if you notice, we can actually multiply some of this out and then combine like terms. So we have x plus 3 raised to the negative 1/2, and then simplifying the inside of this one, we have x plus, and then 2 distributed to the x is 2x, so x plus 2x is 3x. 2 distributed to the 3 is 6, and there we go. That looks much better. So now we can actually start solving for the 0. We can take this negative exponent and put it to the denominator and rewrite it as a fraction. So actually we can drop this parenthesis. So 3x plus 6 over, and then the square root of x plus 3 equals 0. So another thing with fractions is that the only time they're equal to 0 is when the numerator is equal to 0. So the only time this is going to work is when 3x plus 6 is equal to 0, which we know is only when x equals negative 2. If we plug in negative 2, it is equal to 0. If we set the denominator equal to 0, we won't find where the whole fraction is equal to 0. We will find where the fraction is undefined, or when it's over 0. So x plus 3 equals 0 when the inside of the radical is equal to 0, which is when x equals negative 3. So this fraction is only defined where x is equal to anything except negative 3, because that's the only place where the denominator is going to be equal to 0, and dividing by 0 is a big no-no, but the zeros for this are just x equals negative 2. As long as x does not equal negative 3, we are good. Moving on, this one is probably one that looks more familiar because there's an x squared and x in a number. So making this, factoring this, we can first of all take out a 3 from all these terms, and I'm just going to take out a negative 3 because I don't like negatives on the leading coefficient. So negative 3, if we take that out of everything, we get this, and if you want to check that, you can just distribute it back in, and we'll see that it's the same. So now we just have to factor this inside part. So we have a 2x and an x. The reason I set that up like that is because the only way to get to 2x squared is multiplying 2x and x. But now our task is to figure out what these numbers are here and what the signs on them are. So what informs me from here is looking at this last number, this negative 12. These two numbers have to multiply to equal negative 12. So the first thing with that, to multiply to a negative number, you have to multiply a positive and a negative. So we know that either there's a plus here and a minus here, or a plus here and a minus here. So I'll just note that one of them is plus, one of them is minus. And the other thing is that it has to multiply to 12. So it can either be 1 and a 12, 2 and a 6, 3 and a 4, 4 and a 3, 6 and a 2, 12 and a 1. Any of those combinations with any of those combinations, one of them hopefully will come out to negative 5 when we actually FOIL it. So the last thing, because we don't really want to plug in all of these because that would be 12 tries until we found the right one. If we look at this, we can kind of inform our decision as far as what numbers and where the signs go for these. So it's negative 5x. So the outer and the inner, we add the two numbers, and if you add something and you get something negative, if it's a plus and a minus, you would know that the minus is larger than the plus. So I'll just make a note of that. I'll say big or bigger. So that minus is going to be larger because what we have in the middle is a negative number. So that's about all we can get. That informs us here. So now we just have to trial and error until we get the right one. So what I'm going to do is, since this is a little bit negative, not like if we did 2 times 12, that'd be 24, but this is 5. So probably not that extreme, but more of these middle couple. So I'll try putting a minus here and a plus here, and going 4 and 3. So let's check that. We get negative 8 and positive 3. So we did it. So that's negative 5. and we got the -3 here, and there's your answer. In this last example we have 2x squared plus 12x plus 9. Factoring that, if we actually, so we have a 2x and an x like the one we just did. That's the only way we can get to 2x squared. But you'll notice the only thing you can get multiplied to get to 9 is 3 times 3 and 9 times 1. So both of these, first off, both these signs have to be positive because that's positive and that's positive. But either we have a 9, 1, 3 here or a 9, 1, 3 here, and you can check it, but none of those work to get us to our magic number 12. So at this point, you could use the quadratic formula, but a little trick or a faster way is called completing the square. So maybe this sounds like a foggy memory to you, but I'll just go over that here. So you take these two terms with x's in them, and they both have a 2, so let's take that out, 2. And then we have x squared plus 6x, I'll leave a little space there, and plus 9. So right now this is still the same thing that we have. Actually this is, there we go. There we go. So right now this is the same thing that we have up here. If you distribute everything in, you'll end up with what we started with, which that's good because this is algebra. We don't want to change anything around. That's kind of the rule. But we are actually going to intentionally add to this side so that we can complete the square and then go from there. So completing the square means completing the perfect square binomial. So, you know, a plus b squared, that's the perfect square that I'm talking about. So, sure, I'll write that. A plus b squared equals a squared plus 2ab plus b squared. This is what we have here. So a would be x. So if we rewrite this as x squared plus 2bx plus b squared, now we just have to figure out what this term is right here. And if we look, 2b is equal to 6, and so b would be equal to 3, and then 3 squared is 9, so we just put this 9 here. At this point we have changed the left side of the equation because we put the 9 there, so we would have to add what we did over here to this side. It's actually not a 9 because we have this 2 out here distributing to it, so we have an 18, and there we go. So now these are still the same. We just did what we did over here to this side. And from here on, I won't actually solve the rest of it, but all you do is just push everything to the right and factor this actually to x plus 3 squared. And then you push everything to the right and take the square root and solve for the 0. But for the sake of time, that's just completing the square, is using this logic on this and adding an actual number to the left side, but adding the same number to the right, and then you can proceed. Instead of having to do the quadratic formula up here, you can complete the square like this. So the last bit that we have are log rules. Log rules are kind of an inverse or opposite of exponent rules. So if you look, a to the x equals b, writing that as a log instead of an exponential kind of expression, we would have log base a of b equals x. So with concrete numbers, if I said, what power, if I raise 5 to what power will get me to 125? And you would say, oh, I just take the log base 5 of 125 and I find out that it's 3. And then you just chuck this 3 back in for x and see that 5 cubed is 125. So just have that in the back of your head. That'll give you a little intuition as to why these log rules work out the way that they do. But anyway, so log base b of a product of two things is log base b of the individual things added together. So log base b of m plus log base b of n. And this similarly, like we had with exponents, with the subtraction, the fraction subtraction, we have log base b of m minus log base b of n. We can split that into two different logs. And here we have log base b of a number to a power. We can take this power and move it out to the front as a coefficient on the log. So m to the k becomes k times log base b of m. And right here, just something to always know is that log base anything of 1 is always going to be equal to 0. And something else I'd like to say here, on the AP test, they try and trick you with writing answer options in different forms of what you have after doing all your stuff by hand. So say you got out some expression and at some point in the answer there's like ln of 1/3. And you notice in the answer options they don't have what you have, but they do have negative ln of 3. Well, those are actually the same thing. So they're going to try and make it seem like you did something wrong when you actually didn't, which should be a criminal offense, I know. But have the presence of mind to be flexible and be able to split this into ln of 1, which is 0, minus ln of 3, and the ln of 1 just goes away and becomes minus ln of 3. So I'll just write that out. ln 1 minus ln of 3. These two are the same, and these two are the same. These three are all equivalent expressions. The ln of 1 just goes away because that is equal to 0, and so these two are the same. So don't get tripped up on that during the test. And one last useful trick with logs is the change of base. So if I have log base 3 of 604, and I, for some reason, have an issue with the way it is right now, I could rewrite this as log base anything. I'll just do log base 10. You could rewrite this as log base 10 of 604 divided by log base 10 of 3. It could be ln of 604 over ln of 3. This one you don't see it quite as often as these, but having that in mind is also useful. And then one last quick little example here, ln of y equals x plus 2. So if we want to get this into a more desirable form like y equals, the last log rule that we can apply, if I have e raised to an ln of some number, let's say b, or if I have ln of e raised to some number b, since these are inverses, ln and e are like inverses of each other, they could cancel each other out and you just end up with b. That's for both of these. So if we apply what we learned here, down here, we can go e and raise e to both of these. Since we do it to both sides, it's still the same thing. But now we have e to the ln of y, and these are inverses, so we can cross those out, and we have y equals, and that's much more familiar than ln of y equals. But now we have a rough idea of what the graph looks like instead of some alien expression up there. And this last example problem will kind of synthesize everything we've learned so far. So here we go. So we want to see where this is equal to 0. So right now it's kind of icky, and we can do stuff to it to make it look pretty. So let's do that. So we have an e to the x plus 1, e to the x plus 1, e to the x. This isn't, the exponent isn't x plus 1, sorry. It's e to the x plus 1. But anyway, we can take that out using our factoring skills from both of them, and if we distribute that in, it would look like this is still the same thing. You can check it by factoring or check it by multiplying everything through, but if we take out an e to the x plus 1, this is what we are left with in the numerator, and then in the denominator we have the same thing. The point of that was because now we can subtract this 1 minus this 4, and we're left with e to the x plus 1 cubed on the bottom, and this thing can be simplified. So now in our numerator, if this goes away, I'll just faintly cross that out, 3. This is going to turn into, if we distribute 2x e to the x plus 2x e to the x plus 2x minus 6x e to the x. That's still the same. And on the bottom we have e to the x plus 1 cubed. And we can combine like terms. Sorry, this is equal to 0, equal to 0. We can combine like terms in the numerator. X e to the x e to the x. 2 minus 6 is negative 4x e to the x plus 2x over e to the x plus 1 cubed. So at this point we can start solving. Like the fraction that we looked at earlier, this is only going to be equal to 0 when the numerator is equal to 0, and that's the same with all fractions. But also keeping in mind that whenever the denominator is equal to 0 is when the fraction is undefined and there are discontinuities in the graph. So let's do the denominator first. E to the x plus 1 cubed equals 0. This is only going to be true when this inside part is equal to 0. So if this inside part is equal to 0 and we cube it, that's not really going to do anything. still going to be 0, so we can rewrite this as e to the x plus 1 equals 0. So hopefully that made sense. Cubing 0 still makes it 0. So this and this, whatever comes out is still going to be the same. You can check if you'd like. But now what we have, we can subtract this 1, e to the x equals negative 1. So now our task is, when does e to the x equal negative 1? Flashback to my earlier video on tips and tricks for Calc. One of them was visualize the graph, or be able to connect between functions and graphs. So here the function is e to the x, and if we connect that to its graph, I'm going to go over this more in the functions and graphs video, but this is roughly what the graph of e to the x looks like. But the thing that I would have in my mind is that the range of e to the x is that it's always greater than 0. So e to the x is never less than or equal to 0. We can just look, eyeballing this graph, obviously, it never touches the x-axis. It gets infinitely close, never touches. But from this graph, we can notice that e to the x will never reach the value of negative 1, since that's below the x-axis and it never goes below. So from that information, we know the denominator will never equal 0, and there won't be any discontinuities in this graph. So from there, we can look at the numerator now, negative 4x e to the x plus 2x, and where that is equal to 0 is where that whole fraction is equal to 0, because it's the numerator. So now we just have a couple more factoring tricks to go through. What I did was take out a negative 2x because we have an x, and both of these are positive, and I just took out the negative because it irks me that that would be in the front number. But now you can obviously check whenever you're going through factoring problems, multiply through and check your work. So negative 2x times 2e to the x is that, and then that is that. But now we have basic factoring 101, solving for zeros. This is going to equal 0 when either this is 0 or, when this is 0 or when this is 0. So the thing behind that is just, if you have a 0 here and anything there, this is still going to be 0, because 0 times a number is 0. And the same argument can be made if this is 0 and this is any number. So we solve for the two independently. So where is this equal to 0? Well, where this is equal to 0 is when x equals 0. So that's one of our zeros, is x equals 0. And now we just have that one. So 2e to the x minus 1 equals 0. That's going to happen if we add this 1 over and divide both sides by 2. We would have e to the x equals 1/2. Hopefully that wasn't too much mental math, but being flexible like that will help a lot, take less time on the calc tests. Anyway, so looking at this graph again, we know that this at some point will equal 1/2, but where? Well, if we remember our log rules, or our natural log rules, if you take the natural log of this whole thing, or both sides, this is log base e, and this is base e raised to an exponent, so those two cancel, and you can just write the exponent x. And since we're doing it to both sides, we have ln of 1/2. To even further simplify, if we remember our log rules, we can take this fraction and turn it into subtraction. So x equals natural log of 1 minus the natural log of 2. If we remember again, natural log of 1 equals 0, so we have x equals negative ln of 2 as our final answer. And that was kind of the behemoth final problem that we had, but good job. So thanks for sticking through the whole thing. Hopefully you didn't learn anything, because hopefully you had all of it down already. But anyway, this was just a review of algebra stuff that you should know, or that's really useful for calc. And in the future we'll have functions and graphs, geometry, and trig. So stay tuned for those, but there you go.